Designing and building any kind of mechanical system is a complex process that needs to properly account for many different parameters, like cost, materials, and manufacturing techniques. But one of the key challenges is making sure that all of the parts, once manufactured, will fit together and function as intended. And that's why tolerancing is such an important part of the mechanical design process. The easiest way to define tolerances is using the dimensional approach, where drawings define how much each dimension of a part is allowed to deviate from its nominal value. But dimensional tolerancing doesn't work particularly well in a lot of scenarios, because it doesn't really reflect how the part will be used. It doesn't let you specify that you need a surface to be flat because it has to create a seal with another part, for example. Or let you control how close to perpendicular the axis of a hole needs to be to the surface it's drilled into. Geometric dimensioning and tolerancing, usually called GD&T, is a different approach to tolerancing that allows you to control tolerances in a way that reflects the intended function of the part. It complements dimensional tolerancing by letting you control 14 different geometric characteristics, helping you better communicate which aspects of your design are important. These characteristics can be split into categories that control form, orientation, location, profile, and runout. Unlike the traditional tolerancing approach that applies tolerances to dimensions, GD&T applies them to features instead. A feature could be a surface, a hole, or a slot, for example. It's important to differentiate between surface features, which are just individual surfaces, and features of size, which are any features that have a defined dimension, meaning that they can be measured with calipers, whether that's a hole or a feature defined by two opposed parallel surfaces. This is because in the GD&T world, geometric tolerances can mean very different things if they're applied to surface features or to features of size. Geometric tolerances are assigned to features using feature control frames. These little grids contain all of the information needed to fully control a particular geometric characteristic. They can be applied to features using leader lines, extension lines, or for features of size, they can be attached directly to dimensions. Let's look at how they're structured. The first box in the frame contains a symbol that defines which of the 14 geometric characteristics is being controlled. The next box specifies the tolerance to apply. This value defines the size of a tolerance zone within which the entirety of the feature must be located. The shape of the zone depends on the geometric characteristic being controlled. A diameter symbol can be added to indicate that the tolerance zone is circular or cylindrical. Next is a series of letters that defines datums, the reference surfaces that need to be considered during inspection. And finally, modifiers can be added to either the tolerance or to the datums to get even more control over tolerancing. We'll talk about datums and modifiers in more detail later on, but first let's look at an example, starting with one of the simpler geometric characteristics, flatness. The feature control frame for a flatness callout looks like this. When the callout is applied to a surface, it defines a tolerance zone between two parallel planes that are separated by the distance shown in the feature control frame. All manufactured parts are imperfect. For a part to meet this tolerance, all points on the surface must be located within the tolerance zone. The two planes defining the tolerance zone are parallel to each other, but they don't have to be parallel to any other surfaces. Flatness tolerances are often specified on surfaces that mate with other parts, and need to have even contact, like the face of a flange. Flatness